Backpropagation and convolutional neural networks, CNNs, are fundamental components of modern deep learning, particularly in the field of computer vision. Let's break down how they work individually and then see how they come together in CNNs. Backpropagation. Backpropagation is a training algorithm used to optimize neural networks. It's a supervised learning technique that adjusts the model's parameters, weights and biases to minimize the error between predicted and actual outputs. Here is how it works. Forward pass. In the forward pass, input data is passed through the neural network layer by layer, and the network's predictions are calculated. Loss calculation. A loss function, e.g., mean squared error or cross entropy, quantifies how far off the predictions are from the actual values. Backward pass, backpropagation. This is the key step. Backpropagation calculates the gradient of the loss function with respect to each parameter in the network. It starts from the output layer and goes backward through the layers. The chain rule from calculus is used to compute these gradients. Gradient descent. After computing the gradients, a gradient descent optimization algorithm is employed to update the model's parameters. The idea is to adjust the parameters in the opposite direction of the gradient to minimize the loss function. Repeat. Steps 3 and 4 are repeated iteratively for multiple epochs until the model converges, i.e., the loss is minimized or reaches a satisfactory level. Convolutional neural networks, CNNs. CNNs are a type of neural network specifically designed for processing grid-like data, such as images and videos. They are exceptionally well suited for tasks like image classification, object detection, and image segmentation. Here is how they work. Convolutional layers. CNNs consist of convolutional layers. These layers use filters, also called kernels, to scan the input data in a sliding window manner. The filters' weights are learned during training. This operation helps extract local patterns and features from the input. Pooling layers. After convolution, pooling layers are often used to downsample the feature maps. Max pooling and average pooling are common pooling operations that reduce the spatial dimensions of the data while retaining important information. Fully connected layers. After several convolutional and pooling layers, one or more fully connected layers are usually added. These layers take the flattened feature maps from the previous layers and perform traditional neural network operations. Activation functions. Nonlinear activation functions like ReLU, rectified linear unit, are applied after each layer to introduce nonlinearity into the model. Backpropagation. CNNs use backpropagation to update their weights during training, just like traditional neural networks. The backpropagation process helps the network learn features and patterns from the data that are relevant to the task. Output layer. The final layer in a CNN typically has as many neurons as there are classes in the classification problem, and it uses a suitable activation function, e.g., softmax for classification, to produce the final output probabilities. In a CNN, the convolutional and pooling layers help capture hierarchical features in images, recognizing simple patterns like edges in lower layers and complex patterns like object paths and objects themselves in higher layers. The backpropagation algorithm is used to adjust the weights in all layers of the network, allowing it to learn representations that are useful for the given task, such as image classification. Hope you like this content. Please like, comment, share and subscribe as well.